Now we will study how to design a domestic water supply system using available municipality water supply pressure and without use of any transfer or pressure booster pump. We already studied how to design the water supply piping inside the building. I will provide the link in the description. Now we will study how to design the riser and main line. We have available pressure from municipality water supply line equal to 60 psi, and we will design the domestic water supply system for a 4-story building. We will do our design study for a building having 4 number of floors, each floor height 10 feet and each floor having 10 number of apartment. This building has 5 number of water supply risers R1, R2, R3, R4, R5, and each riser is supplying water to 2 number of apartment on each floor. To design the domestic water supply system by available municipality water supply pressure, first of all we need to calculate the available friction loss per 100 feet to design the water supply piping for the system. To calculate the available friction loss per 100 feet, we need to follow these steps. Number 1. First of all, we need to determine the available water supply pressure from municipality. Number 2. We need to select the pressure required at the highest fixture. Number 3. We need to calculate the total pressure drop inside the system. Number 4. We need to select the pressure drop inside the devices that are available in the system. Number 5. We need to calculate the longest developed pipe length. Number 6. Finally, we need to calculate the allowable friction loss by this formula: available pressure minus total pressure drop into 100 divided by longest developed pipe length. After calculation of allowable friction loss, we will design the total water supply system for the building, following the same step as we already done in our previous video for high-rise building. Let us now calculate the pressure drop inside the system. We have the formula for pressure drop inside the system. It is equal to pressure drop due to elevation change, that is due to lifting water from ground to high level, plus pressure drop inside the piping due to friction loss when water is flowing through it, plus pressure drop due to devices when water flowing through the devices. Let us first calculate the pressure drop due to elevation difference. As we are doing this calculation for a building of 4 floors, each floor height is 10 feet, then the total height for floor is equal to 40 feet. As we know the formula, pressure drop due to each foot of vertical rise is equal to 0.434 psi. Then the total pressure drop due to elevation difference of 40 feet or vertical rise of water to 40 feet will be equal to 0.434 into 40, and the result will be 17.36 psi. As we are using 2 devices with our water supply line, one water meter and one backflow preventer, pressure drop inside water meter is equal to 3 psi and pressure drop inside backflow preventer is equal to 1 psi. If you are using other devices also with your water supply line, then you need to consider the actual pressure drop inside that device when water is flowing through it. For pressure drop inside water meter and backflow preventer, you need to select the actual pressure drop value from the brochure that will be supplied by the manufacturer or supplier. At this stage, we will not calculate the pressure drop inside the pipe due to friction loss, as now we are calculating the allowable friction loss for the pipe. Then the total pressure drop inside the pipe is equal to 17.36 due to elevation difference, plus 3 due to pressure drop inside the water meter, plus 1 due to pressure drop inside backflow preventer, and it will be equal to 21.36 psi. Let us now calculate the longest developed pipe length. Longest developed pipe length is calculated by determining the overall piping distance from the water main up to the most remote fixture having maximum number of water supply fixture unit. Also, we need to consider all fittings and wall in the critical path. At this stage, it is time consuming to calculate the friction loss inside all fittings and walls. Also, we are not sure when we will make the final installation. We will follow the exactly same route as now we are designing. So it is good practice to add 15 to 50% of the overall piping distance to compensate the friction loss inside the fittings and walls. We will consider for our study 25%. So the longest developed pipe length will be equal to total length into 1.25, and total length in our case is 280 feet. So 280 into 1.25 will be equal to 350 feet. So the longest developed pipe length will be equal to 380 feet. Finally, we will calculate the allowable friction loss. We have 60 psi available pressure from municipality water supply. 30 psi pressure we need at most remote fixture, and we already calculated total pressure drop inside the system equal to 21.36 psi. Then the total losses is equal to 51.36 psi. Then we will calculate allowable friction loss by this formula: total available pressure minus total losses into 100 divided by longest developed pipe length. In our case, it will be 60 minus 51.36 into 100 divided by 350. Then we will have the allowable friction loss equal to 2.5 psi per 100 feet. Now we can use 2.5 psi per 100 feet pressure drop rate to select the pipe sizing for this building. Let us now design the water supply piping network for this building using calculated allowable pressure drop. It is one of water supply riser supplying water to this building. You can see there are 4 branches coming out from this riser and going to each floor. Each branch is supplying water to 2 number of apartment. So the top portion of this riser is supplying water to 2 number of apartment, and the load value here is 17.2 water supply fixture unit. When we come down one level below, then this segment of this riser is supplying water to 4 number of apartment, to here and to here, and the load value here is 34.4 water supply fixture unit. When we go down last level ground floor, then this segment of this riser is supplying water to 8 number of apartment, and the load value here is 68.8 water supply fixture unit. So we can divide this riser into 4 pipe segment 1, 2, 3, 4, each segment having different load value, and it will result different GPM and different pipe size. And the total load value for this riser is 68.8 water supply fixture unit. Let us assume all risers are typical. Then the riser at the end will decide the critical path, or it will have the maximum pressure drop or longest piping route from the last fixture up to the water supply source. So let us highlight the critical path. It will start from riser 5 up to the water supply source. As we have seen, load value at the bottom of the riser is 68.8 water supply fixture unit. As we will go along the critical path, when another riser is connected to the critical path, the load value will increase. So we can divide the critical path into different pipe segment having different load values. The first pipe segment has load value 68.8 water supply fixture unit. As we have given tag number in the riser from 1 to 4, so we'll start tag number in this critical path from 5. Then another riser is connected, riser number 4, to the critical path. Then the load value will become 137.6 water supply fixture unit. We will give it tag number 6. Again, riser number 3 is connected to the critical path. Then the total load value will be 206.4 water supply fixture unit, because there will be 3 riser connected and one riser has 68.8. So 68.8 into 3 will be 206.4 water supply fixture unit. From this side also there are 2 risers. When all 5 riser is connected, the total load value will be 344 water supply fixture unit, and we will give this pipe segment tag number 8. In order to calculate the GPM and select the pipe size, let us make a table in Excel for all the pipe segments with their load values. We will calculate GPM using table AP103.33 of International Plumbing Code. This table is divided into two portions. The right hand side portion is if you are using flush valve for flushing system, then you need to calculate your GPM using this portion. If you are using flush tank for flushing system, then you need to use the left hand side portion. We are using the flush tank system, so we will calculate our GPM from this portion. The first column is showing the load value in water supply fixture unit, and the second column is showing the GPM corresponding to the load value. But when we will select the GPM using table AP103.33 for our selected load values, we will face one problem. Our calculated load values are 17.2, 34.4, 51.6. But the load values in table AP103.33 are 1, 2, 3, 4, 5. For 17.2 we will not find, we will find for 17 and 18. For the same 34.4 value we will not find, we have value for 30 and 35 water supply fixture unit. We have one load value 51.6, but you can find here 50 and 60. There is no 51.6. In order to solve this problem, we will use linear interpolation formula to find the GPM for our calculated load values. Our first load value is 17.2, so we will select the GPM for it. For 17 water supply fixture unit, we need GPM 18.4, and for 18 water supply fixture unit, we need GPM 18.8. Applying linear interpolation formula, we need the GPM for 17 water supply fixture unit, it is 18.4, and for 18 water supply fixture unit, we have the GPM 18.8. Then for 17.2, we will need the GPM 18.48. Second load value is 34.4. Let us select the GPM for it. For 30 water supply fixture unit, we need 23.3 GPM, and for 35 water supply fixture unit, we need 24.9 GPM. Similarly, for 34.4, for 30 water supply fixture unit, we have the GPM value 23.3, and for 35, we need the GPM 24.9. Then the GPM needed for 34.4 water supply fixture unit will be 24.708. In the same way, we can select the GPM for all the load values. Let's fill all the calculated GPM value in this column. Before starting the selection of pipe size, we need to decide the material of the pipe. For our study, we will use the copper pipe type K. To select the pipe size, velocity and pressure drop, we will use the hydraulic table from Engineer Plumbing Design Handbook. Each pipe size has its own hydraulic table. This table is for a pipe size 1¼ inch. The first column is for the GPM, and there are other columns as per the material. You can see this column is for schedule 40 steel pipe, this for schedule 80 steel pipe. We are using copper pipe type K, so this column is for us. Inside this column also you see there is two sub columns. The first column is for the velocity in feet per second, and the second column is head loss PSI per 100 feet. As the pipe sizes in hydraulic table is given only for standard values of GPM, so again we will use the linear interpolation formula to select the pipe size, velocity and pressure drop for our calculated GPM values. For domestic water pipe sizing, we follow these rules. For cold water piping, the maximum velocity limit is from 4 to 8 feet per second, and the maximum pressure drop limit is 5 psi per 100 feet. For hot water piping, the maximum velocity limit is 5 feet per second, and the pressure drop limit is 5 psi per 100 feet. Our first GPM value is 18.48. Let us select the pipe size, velocity and pressure drop for it. Our first GPM is 18.48. So let us first try to select 1 inch pipe size. So we will use the hydraulic table for 1 inch pipe. Here you can see we have a value for 18 GPM and for 20 GPM. For 18 GPM, let us select the copper pipe type K. So the velocity will be for 18 GPM 7.42, and for 20 GPM the velocity will be 8.24, which is more than the maximum limit 8 feet per second. When we see the head loss per psi per 100 feet, for 18 GPM this is 11.9, and for 20 GPM this is 14.5. These both value are much higher than the maximum limit, which is 5 psi per 100 feet. So we cannot select the 1 inch pipe size. Then we will go next pipe size, which is 1¼ inch. Now it is the hydraulic table for the pipe size 1¼ inch. We can find here 15 GPM, and the velocity for 15 GPM for copper pipe type K is 3.95, and for 20 GPM it is 5.26, which is less than the limit 8 feet per second. When we see the head loss, it is for 15 GPM 2.9, and for 20 GPM 4.9. Both values are less than the maximum limit, which is 5 psi per 100 feet. So for 18.48 GPM, we can select the 1¼ inch pipe. To select the exact pressure drop and velocity, again we will use the interpolation formula. For 15 GPM we have the velocity 3.95 feet per second, and for 20 GPM we have the velocity 5.26. Then for 18.48 we will have the velocity 4.86. Similarly, for 15 GPM in 1¼ pipe we have pressure drop 2.9 psi per 100 feet, and for 20 GPM we have pressure drop 4.9 feet per 100 psi per 100 feet. Then for 48.48 GPM we will have a pressure drop of 4.29 psi per 100 feet. The GPM for the second pipe segment is 24.71. Let us select the pipe size, velocity and pressure drop for it also. For 24.71 GPM, let us select the 1½ inch pipe. Here we have 20 GPM and 25 GPM. For 20 GPM, we have the velocity for copper pipe type K 3.72, and for 25 GPM we have the velocity 4.65. Both are in the range. Then head loss psi per 100 feet. For 20 GPM it is 2.1, and for 25 GPM it is 3.2. So we will select the 1½ inch pipe for 24.7 GPM. For exact value of velocity and head loss, again we will use the interpolation formula. For 20 GPM the velocity is 3.72, and for 25 GPM the velocity is 4.65. Then the velocity for 24.71 will be 4.596, or we can take it 4.6 feet per second. Similarly, for head loss, for 20 GPM we have the head loss 2.1 psi per 100 feet, and for 25 GPM we have the head loss 3.2. So for 24.71 we have the head loss 3.136. It means 3.14. Let us fill the value of selected pipe size, velocity and pressure drop for both these GPM, and in the same way we can select the pipe size, velocity and pressure drop for the remaining GPM using the hydraulic table. We have selected GPM, pipe size, velocity and pressure drop for all the pipe segment. Let us now fill the value for the pipe segment length. As we know, in riser all pipe segment is of 10 feet length. So we will fit 10, 10, and we have 4 pipe segment in the riser. Then the horizontal length is segment number 5 is 60 feet, and segment number 6 also 60 feet, and segment number 7 is 60 feet, and segment number 8 let us assume 30 feet. Now this column will give the total pressure drop in that pipe segment. Let us assume the piping length inside the building up to the last fixture is 30 feet, and it is selected at the rate of 2.5 psi per 100 feet pressure drop. Then it will give the total pressure drop value 0.75. How to select the pipe size inside the building we already studied. I will provide the link in the description for this video. So now we have calculated the total pressure drop, which is equal to 5.735. Let us add 25% of it as the pressure drop inside fitting and walls. Then the total pressure drop in the system will be 8.6025. As we have already calculated, the allowable pressure drop is equal to 8.64 psi, and our calculated pressure drop inside the system is 8.60, which is less than the allowable total pressure drop. So it means our design is acceptable. So in this way you can design the domestic water supply system for any building using available municipality water supply pressure. If your calculated total pressure drop value is more than allowable total pressure drop, then you can reselect the pipe size using lesser pressure drop rate. But if still this total pressure drop value is more than the allowable total pressure drop, then you need to select the booster pump for the difference between total pressure drop and the allowable total pressure drop. I will advise you to watch my previous two videos. First, how to design the domestic water supply piping inside the building, and the second, how to design the domestic water supply system and selection of booster pump for high-rise building. I hope this video will help you how to design the domestic water supply system for a building. Thank you very much.